Yes.
Okay, so thanks very much for the invitation to speak. I'll tell you about some work I've been doing lately on applying these ideas from machine learning to Calabi-Yau manifolds. So I took my title, Precision String Phenomenology, and I gave it to ChatGPT and asked it for a picture. And this is how it interprets precision string phenomenology. And I tried it again, and it gave me this picture. So it seems like it doesn't know what phenomenology is to an extent, and knows what string theory is. And I'm not sure about precision, but this is what we have. Any case, this is a small audience, so please do stop and interrupt me when you have questions. I really enjoy it if it was a conversation rather than a monologue, so don't hesitate. Um, the motivation behind this work is really phenomenological in that we are chasing the real world, and the objective is to obtain this from a string compactification. So we have some first principles realization of particle physics and cosmology as we see it in four dimensions. So a starting point is a modestly unreal world, so the MSSM, or some variant thereof. So you want to have n equals 1 supersymmetry in four dimensions with the right gauge group and the right matter structure and the right kinds of interactions, along with three generations of particles such that the couplings are identical. And we want the structure to be consistent with cosmology. So to have n equals 1 supersymmetry in four dimensions, it's already enough to start off with a Calabi-Yau manifold, Calabi-Yau threefold, as a compactification geometry. This is because it admits a Ricci-flat metric. And the Ricci-flat metric solves the Einstein equations, and it gives us a nice enough theory to work with in four dimensions. So to have n equals 1 supersymmetry in 4D was already the starting point back in the 1980s. And then you use topological and geometric features of the Calabi-Yau to recover aspects of the real world. So the topological features, for example, are the simplest kinds of constructions. If you take the difference between the Hodge numbers H11 and H12, which count the number of cycles of various dimensions on the Calabi-Yau, we're able to get the number of generations of particles in the low energy spectrum. So you're able to match aspects of low energy particle physics to higher dimensional geometry. So the idea of applying machine learning to data sets in string theory really happened in the mid around 2017, 2018. People started doing this, and one of the first things that I looked at was to try to understand whether the topological features of a Calabi-Yau can be machine learned. So in particular, we have 7,890 so-called complete intersection Calabi-Yaus. These are realized as the zero locus of a set of polynomials in products of projective space. And from the configuration matrix describes these equations, we can read off the Euler character fairly easily. And then the H11 varies between 0 and 19, while H21 varies over a larger range. So we chose to machine learn H11 using different kinds of machine learning architectures. Neural network regressors, neural network classifiers, and support vector machines are the ones we initially played with. And we found that using the traditional 80% training, 10%, 20% testing division of these data sets, we're able to learn H11 to reasonably high accuracy. These were initial experiments that were done with very simple machine learning architectures. Since our initial work, the work of others, notably Urban and Finatello, have gotten these accuracies up to essentially 99%. So we're able to machine learn topological features of Calabi-Yaus with high degree of accuracy. So the larger data set to study are Calabi-Yaus are realized as hypersurfaces and toric varieties. And Banarev and Borisov gave a prescription for how to obtain such geometries, starting from so-called reflexive polytopes. There are 4,319 reflexive polytopes in three dimensions, and these all give K3, but there are 500 million polytopes in four dimensions, and this gives a set of Calabi-Yaus with 30,108 pairs of Hodge numbers H11 and H21. We don't know how many polytopes there are in more than four dimensions, There have been a number of polytopes have been constructed, but this list is far from exhaustive, and numerical, dimensional analysis and numerology indicate these numbers can be as high as 10 to the 18. So it's difficult to, certainly impossible to construct a complete data set, but we can start playing with the amount of data we have, and this is certainly in the realm of big data. So one of the things we found in playing with these 4D polytopes was a new formula for the Euler characteristic for threefolds. And this is related to the number of points on the polytope, the dual polytope, and scaled up versions of these. Recently, we've also been able to construct new polytopes in 5 dimensions with new Hodge numbers and designer properties for phenomenology using genetic algorithms. And this is work with Ellie, who's in the audience. And we've also looked at taking explicit triangulations of these geometries to construct non-singular Calabi-Yaux. And this is more work with Ellie, who's in the audience. So we're able to go from these polytopes to toric Calabi-Yaux to play with. So this is an advance in understanding where these geometries come from and understanding the topology of Calabi-Yaux spaces. We'd like to do better than topology. We'd like to move on to geometry. And the difficulty is that Yau's theorem, which established the existence of Calabi-Yaux spaces and the validity of Calabi's conjecture, is not constructive. So the difficulty then is to define these metric quantities and learn geometry and use this geometry and apply it to problems in phenomenology or problems in mathematics. So what Yau showed was by solving a classical Monge-Ampere equation, when a solution exists, which he's able to establish when the first Chern class vanishes, the conjecture that there is a Ricci flat metric in each Kähler class is satisfied. But the proof that Yau gave us in 1977 is not going to tell us what this metric is. So we need to use numerical methods to push further. So you might ask, what do we need a metric? You know, we already have, as I said earlier, a number of Calabi-Yaux bactifications that reproduce aspects of the Stern model. So that is to say, they've got the correct matter spectrum interactions. And this is work from the mid-2000s that showed these realizations of Stern model-like physics from these string compactifications heterotic explicitly. But if you want to go beyond just knowing what interactions there are and computing the actual interaction strengths, you do need the metric. So in particular, the kinetic terms from the Kähler potential for matter require knowledge of the Ricci flat metric. Computing Kähler couplings in a general case require knowledge of the Ricci flat metric, and we'll discuss what we can do in this regard later in the talk. We were after things like moduli stabilization in order to get good cosmological solutions. And KKLT-like models, for example, in de Sitter space, require knowledge of the metric to show that these solutions are stable. We also know the string theory is alpha prime corrected order by order, and understanding these corrections requires knowledge of the metric. And finally, we don't know very much about supersymmetry breaking, but in order to understand the actual real world rather than these model unreal worlds, we may need to know something of the geometry of Calabi-Yaux compactification. So as I said, to date, the best we can do is numerical approximations of the flat metric on the threefold. The attempts to construct such flat metrics have a long history. They also started in the early 2000s with papers by Hedrick and Wiseman and by Donaldson. The best numerical approximations that exist right now are the ones that are machine learned. And this program was initiated in 2019 by Ashmore, Hay, and Overett, who used machine learning to develop and augment the Donaldson algorithm. But in 2020, in the late December that year, 3 different groups published machine learning neural network approaches to finding these Ricci flat metrics ab initio. And I'll tell you about our effort in this direction in that COVID year. Since then, these methods have been refined, and we have better algorithms for finding the flat metric, and I'll tell you about that later as well. So the analytic approach to this problem, finding exact expressions for Ricci flat metrics at various points in moduli space, is very difficult. So even for the torus, it was only in 1873 that Clifford wrote down the Ricci flat metric. This is it's surprising it took so long, but indeed it did take that long, even though tori have been known forever. In 2018 and in follow-up papers since then, Castro, Tripathy, and Zimet have come up with an analytic metric on a particular K3 that's singular. And I'll make some comments later on about whether we can compare their analytic results to our numerical results. We'll see the difficulties in making this comparison. So with these general motivations, I'd like to proceed and tell you a little bit about clear section Calabi-Yau in geometry, and then I'll tell you about the methodology for machine learning metrics, and I'll show you some of the Ricci flat metrics that we've learned, and then I'll tell you about how to use this for phenomenology by computing the actual couplings in the low energy effective theory, and I'll discuss prospects for future work and how we can go beyond this. So this is a work in a series of papers with Damian and others who are crucial to this program. Here are pictures of my collaborators. In particular, the people in red were heavily involved in encoding all of this up, and we could not have done this work without the conceptual and the technical insights of these people in developing our Ricci flat metrics and using them. So many of them will be or are on the job market, so please keep an eye out for them. All right, so we'll look at complete intersection Calabi-Yaus, and we'll look first at a family of these. It starts with a torus as a cubic realized in P2, and then K3 as a quartic in P3, along with some deformations of this expression. And then we'll look at the quintic in P4, along with deformations there as well. But we'll also look at more interesting geometries that are realized by more than one equation. For example, the intersection of two cubics in P5. The mirror of this manifold is of interest to us, and then we'll pursue the Tian-Yau manifold. The Tian-Yau manifold has Euler character -18, so a freely acting Z3 quotient of this Tian-Yau gives a Calabi-Yau with chi equals -6, and because 1/2 of the absolute value of -6 is 3, this was of fundamental interest in the early days of string phenomenology, and the first standard model-like theories were built on this particular quotient. So we'll return to this quotient when we compute Yukawa couplings later on in the talk. Okay, so I'll remind you the Calabi-Yau manifold is both complex and Kähler, and the metric can be obtained by taking derivatives of the Kähler potential, and similarly, the Ricci tensor can be obtained by taking derivatives of the log det of the metric. So the metric constructs the 1-1 Kähler form, which is closed, and in machine learning the Ricci flat metric, we use a loss function which is engineered to reproduce the desired features of the metric. So one very simple loss function one can imagine is just taking the absolute value of the components of the Ricci tensor and sum them all up. When that vanishes, we have the Ricci flat metric. The difficulty with such a loss function is when you take derivatives, the act of taking derivatives amplifies the error. So there are cleverer ways of finding the Ricci flat metric than solving for the vanishing of the Ricci tensor directly. Okay, so the first sort of mechanical way of doing this is Donaldson's algorithm. So Donaldson proposed an algorithm to approximate the Ricci flat metric. This will sort of supply the baseline for comparing our numerical results. The starting point in Donaldson's algorithm is the Fubini-Studi metric on the ambient projective space. Using this Fubini-Studi metric, we can pull this back to the hypersurface we're considering, which is embedded in the space, and this metric won't be Ricci flat, as you can convince yourself even for the torus. So given this pullback Fubini-Studi metric as a starting point, we can iteratively construct better and better approximations to the Ricci flat metric that we're after. These are indexed by K, which is a measure of the basis of a degree of holomorphic polynomials over the manifold. So these are sections of line bundles. The number of basis elements grows as a polynomial power of k. So for the quintic, for example, it'll grow like k to the fourth. And the Fabini-Sudi metric in the ambient space is scalar, and it's well understood. So this is our starting point. And by using a Kadara embedding on a projective space, we can systematically develop a metric approximation for this Ricci-flat-Calabi-Yau metric that we're after. The way this proceeds is that we define a so-called balanced metric, and we proceed iteratively using this balanced metric step by step. And as k increases, Tian and Donaldson showed this balanced metric will approach the Ricci-flat metric. The difficulty is because the number of sections grows polynomially, numerical implementations of this are very computationally expensive. And though this has been attempted numerous times in the past, the performance of the neural networks today is better than these numerical implementations of the Donaldson algorithm. So we want to, as well, assess how good we're doing. And we need to impose various measures that enable us to do this. The first measure is a so-called sigma measure. It compares two different expressions of the volume, one which is metric independent and one which is metric dependent. So the metric independent expression is just taking omega wedge omega bar, the top holomorphic and anti-holomorphic forms on the manifold, and integrating this over the manifold. The second expression is taking the Kähler form, which is given to us by the metric we've numerically approximated, using that to compute the volume, and then checking whether this volume matches the previous volume. This is the clever way of alighting the actual computation of the Ricci tensor setting equal to 0, because here you have a metric-dependent expression of the volume and a metric-independent expression of the volume. You subtract the two, take the absolute value, and this figures into your loss function. You also need to ensure that the metric is Kähler. So you impose this directly, and you verify that the Kähler form is closed, and you include this as a component in your loss function. And finally, because you're working in coordinate patches on a manifold, doing differential geometry very explicitly, you need to check that if you have two different coordinate patches, the Jacobian, which takes you from one coordinate patch to another coordinate patch, is compatible. There's another component to the loss function which ensures that this is happening. And the loss function can be a sum of these terms. In addition, you need to impose that you're in the same Kähler class you started out with. So all of these can be included in the loss function, and they can be included in such a way that the loss function exactly vanishes when all these conditions you imposed are precisely satisfied. The implementation of this is using feed-forward neural networks. This is an idea that dates back to Rosenblatt in the Naval Research Lab in the Cornell Aeronautics Laboratory in 1957. Ideas that are variants of the simple perceptron models that Rosenblatt presented famously won this year's Nobel Prize. These are technologies that are of great currency in modern day life. The work of the neural network is accomplished by imposing nonlinearities in mapping from one set of neurons to another set of neurons in this network. So roughly speaking, you have some input vectors that come in, and then you take these input vectors and you feed it to the next level, next layer of the neural network by adding a bias vector to your input and acting with weight matrices. And you do this successively, layer by layer, until you get an answer that you want. The process of tuning the parameters in these layers, these weight matrices and bias vectors components, in other words, are what you use as a way to minimize your loss. And you compare your prediction to the ground truth, the simple examples where you know what the ground truth is. In the case of the Ricci-flat metric, we don't know what the analytic expression is, so we're just imposing that the result we obtain satisfy certain properties that we impose. Okay, so in our initial experiments in this direction, we used a neural network that was coupled to another neural network, and this was implemented in various different machine learning architectures. And the the strategy we used was that a Hermitian matrix admits an LDL decomposition into a lower triangular matrix, diagonal matrix. The first neural network learns the diagonal matrix, i.e., the eigenvalues. The second one learns lower triangular matrix. As an input, we give the points on our space along with the seed metric that we start with on the space, and the loss function's linear combination of the different measures we saw previously. So we'll test the metric that we obtain using an independent set of points that are not used in training. The final thing I should tell you about is point selection. How do we choose the points on the manifold? So there is an algorithm that was proposed by Schiffman and Zeldich and implemented in various ways that give us a fair selection of points on the manifold. So essentially, we take lines in projective space that are uniformly distributed with respect to the symmetries of the Fubini-Study metric in the ambient space. So we choose points in the ambient space, and we draw a line between them, and we see where it intersects the hypersurface. That gives us a selection of points that we start out with. It's possible that we can do better than this, and I'll make some comments on that at the end of the talk as well. In fact, I think that maybe an improved point selection is the best way to have a flatter metric. So if we apply these ideas, the Fermat-Quintic, we get some distribution of points. And if we add deformations to the Fermat-Quintic, for example, a Dwork deformation, we see that these distributions shift as expected. So as a result, yes.
So if improved point selections give you a better estimate of flatness of the metric, how much do you gain by knowing the full neuron survey group of the Calabi-Yau?
How much do I gain by what?
How much do you gain? Because if you have this full group of divisors, the full group of lines of the Calabi-Yau, how much would you gain by knowing this beforehand?
I'll make some comments later. I'll show you some pictures. Maybe you can ask a question afterwards.
Okay.
Okay, so the distribution certainly changes with respect to the shape of the embedded hypersurface. Okay, so even with a small number of points, we can certainly do orders of magnitude better the number of points we train with now than we did in our initial experiments. Even with a small number of points and different training rates, we find that all these measures for the quintic decrease, indicating that we're getting a flatter and flatter metric. A parallel way of finding a metric that we've been playing with a little bit is Ricci flow. So Poincaré famously proved that, proposed that every simply connected closed manifold is homeomorphic to S3, and Perelman famously proved this Poincaré conjecture. In fact, Perelman's result is even more general. He proved something called the geometrization conjecture based on some ideas of Hamilton. The central idea is Ricci flow with surgery. So you think about the metric as being parameterized by some parameter lambda, and the fixed points of this flow are the Ricci flat solutions. So in fact, Perelman, what he did was he augmented the traditional Ricci flow with a dilaton, essentially, an extra function, which made the solutions of the Ricci flow equations, the solutions to the equations of motion of a system, which he called the entropy functional. This is essentially something which is anticipated in string theory. Ricci flow is like the RG evolution of a nonlinear signal model on a string world sheet with a certain target space metric. And Friedan had this idea way back in 1980. And Perelman, in his paper on his proof of the Poincaré conjecture, the first paper, he makes some comments about connections with string theory and his ideas. So with Kähler Ricci flow, you automatically preserve the Kähler class of the metric along the flow. And the equations of motion are a modified flow equation, which includes this dilaton we've introduced, and a backward heat equation. You just solve these two equations simultaneously. You can imagine starting the pullback of the Freeney-Studi metric and solving these equations and having a loss function which encodes the equations of motion. Some of the moral motivation behind this is that we know that machine learning is very, very good at using gradient descent in order to find solutions. And by rephrasing Ricci flow a la Perelman, you're essentially doing a gradient descent in order to solve these flow equations. So we have preliminary results. These preliminary results mostly pertain to the torus. We're able to show that we can get Ricci flow on the torus. Our results are perhaps less convincing for more complicated Claude-Yau spaces. But we hope to say something about this sometime soon. Another way of guaranteeing that we remain the same Kähler.
Can I ask
Yes.
another question?
Yeah, sure.
This slide here. So once you have an algebraic variety, the Fubini-Study metric is sort of fixed, right? And
Yeah.
you do the pullback, you solve these Ricci flow equations. So all this seems to be sort of exact to me. So I'm zero in machine learning. So how does the loss function pick this up?
These ideas were initially implemented in a numerical way of finding solutions to these flow equations by Hedrick and Wiseman. So this is their initial approach back in the early 2000s. So we like to see whether we can encode these equations similarly to what we've done for finding the flat metric using machine learning methods. And the way we may do this, for example, is that in fact, this applies to any set of equations. You have left-hand side minus right-hand side equals 0. Take the absolute value, and you impose that into your loss function. In some sense, solutions to such equations can always be machine learned, at least on some compact subspaces in Rn. Does that answer your question?
I'm still so what are we trying to machine learn, so to say? It's like you have a Fubini-Study metric once you algebraic variety fix. So you have your the quintic with the dot deformation, and until the black bullet point, everything seems straightforward. But my question is, what exactly are you trying to machine learn now?
We're trying to machine learn a solution to a coupled set of differential equations. The way one does this is one includes a loss function, which is designed to vanish on the locus of solutions. So just as, for example, we had two different expressions of the volume, they were subtracted from each other. We can always take any set of equations and take left-hand side minus right-hand side and use that as a loss function. Maybe we can chat about this later.
Okay.
I'll proceed.
My question comes from my ignorance of machine learning, so nothing else. Yeah.
Okay. So another way of guaranteeing that we ran the same Kähler class, like we do with Ricci flow, is to use the so-called phi model. So the phi model, again, starts with a pullback to the Fubini-Studi metric, but then it adds to it dd bar phi. And we can learn phi so that the result is Ricci flat. If phi is globally defined, the metric remains in the same Kähler class we start out with. And this idea is implemented in a code package called CY metric that Larfors, Lucas, Rula, and Schneider put out. We used initially this package for point selection. They have a good point selection scheme that we apply to our own machine learning methods. We found, however, that we can do much better than the phi model. And what we use is a spectral network. The spectral network looks at essentially functions of the coordinates of projective space of points in the manifold, and then we then use this data to learn this phi function. And we implemented this network in our work in 2022, and we find that this is sort of the state of the art these days in finding the metric. So let me show you some pictures. If you compare the phi model in the CY metric implementation to the spectral network, we find the spectral network performs an order of magnitude better, given the same number of epochs for training and the same number of points for training. This is equivalent to about k equals 8 in Donaldson's algorithm. Okay, so one of the benefits of working with Kähler spaces is that most components of the connection vanish. And the non-zero components are the ones that are listed there. And the non-vanishing components of the Riemann tensor are similarly few. So from this, we can write down the Ricci tensor in various curvature forms. And we'll use these curvature forms we compute in order to assess how well we're doing in finding a flat metric. So in particular, what we want to do is we want to compute the Euler density, integrate the Euler density of the manifold, and see how close we get to the Euler character. So a family of manifolds for which we can study this are the cephalou deformations of K3, the defining equations P lambda, and this is singular for particular values of lambda, namely 3/4, 1, 3/2, and 3. The 3/4 and the 1 values correspond to certain orbifold like theories. The value lambda equals 1 is the analytic metric proposed on the singular K3 by Katcher and collaborators. With these different values of lambda, there are different numbers of singularities, 8, 16, 12, and 4, and these singularities of A type. So if you measure the Euler density, you integrate this to get the Euler character on these manifolds, we find that when lambda equals 0, i.e. the space is non-singular, we get 24, the expected result for K3 on the nose. For these singular values, we don't get 24. We get some other numbers. But because of these singularities of A1 type, if you include a factor of 2 for each of these singularities, the numbers in the table recover the expected Euler character. So for example, for 3/4, we have 8 plus 8 times 2 is 24. So this is the behavior of the calculation of this Euler density leading to Euler character for different values of this lambda parameter. So the middle vertical line in each of these plots corresponds to the singular point. And we see that away from the singular point, we do fairly well. But close to the singular point, sometimes we don't do so well. The lambda equals 1 case, in particular, we do badly. So it's very hard to compare our numerics to the analytics. So Abraham, yes.
The previous slide.
Yeah.
So X is a K3 surface that you're looking at.
Yes.
And so this map lambda tends to lambda hash. Is that basically meaning that you set lambda to one of these values, or?
Yeah, I set lambda to one of these values. These are the singular points.
Okay. And here x0 is the modular curve, or what is the x0 here?
X0 is K3 with lambda equals 0.
Okay. Okay. Thanks.
Okay. So we do fairly badly at some of these singular points, and lambda equals 1 in particular, we do very badly. So unfortunately, that's the only place where there are analytics that in principle we could have compared to, and we can't make that comparison directly. The metric that was the analytic metric proposed by Katcher and collaborators is in fact rather complicated. It looks deceptively simple in that, but if you look at unpacking the expressions, it's several pages of text long. So it's not really an easy expression to compare to anyway. Okay, so close to lambda equals 1, we start looking at lambda equals 0.98, and we see that we perform relatively okay in finding the flat metric even in these singular cases. And we do much better than the spectral network near the singularities as well. So how well are we doing with respect to threefold? Well, the quintic is an example we can study, and we find that we're off by about 2% in computing the Euler character. So we know that the 1/2 Euler character corresponds to the index of the Dirac operator, which counts the fermion zero modes, and this is what we compare to the number of generations in the spectrum. So if you're off by 2% for the quintic, and you're considering some phenomenological model on the quintic, you're getting the number of generations wrong. However, in most of the standard model-like theories people look at have Euler characters that are much lower. So as a result, being off by 2% is not so bad. Another thing you can do is on this manifold, which is given by set of defining equations on P3 cross P1, we can look at the metric in two different Kähler classes. And if you take the Kretschmann scalar, which is a contraction of the Riemann tensor, we notice that the histogram, which describes the distribution of this Kretschmann scalar, is different for the different Kähler classes. If you change the parameters to define the same Kähler class differently, the histograms essentially lie on top of each other. So we were able to verify that the metrics, the Ricci flat metrics we obtain, are indeed dependent on the Kähler class. If you look at the Euler density and see how this varies, we notice this also varies depending upon the choice of Kähler class as a function of the complex structure modulus that we introduced into the defining equation. So this is some new investigation of how the metric is really Kähler dependent. And this appeared in a paper earlier this week by myself and my collaborators. So please have a look. All right, so moving on from metrics to utility of metrics, we're going to think about Calabi-Yau compactification. So we work in EA cross EA compactifying the Calabi-Yau threefold. The Calabi-Yau, by definition, has SQ3 holonomy. The commutant in AA is E6, so E6 is our gut group. The fields in our theory transform in 27 and 27 bar representations of E6. The number of such multiplets is counted by H1 and H2. In particular, we have 1-1 forms and 2-1 forms corresponding to generations and anti-generations. The Kala couplings of the 1-1 forms are famously topological. So it's the Kala couplings, the 2-1 forms that we're interested in, the so-called 27 cubed couplings. So again, by definition of the Calabi-Yau, there is a nowhere vanishing holomorphic 3 form. And using this nowhere vanishing holomorphic 3 form, given a 2-1 form, we can define an equivalent 0-1 form. And the unnormalized Kala couplings, which are computed without the metric, these are quasi-topological. They depend on the cohomology class, but not on the actual representative that you choose. We want to normalize these couplings using the Kähler potential in order to get the physical quantities which appear in the effective action. So in the simplest case, we'll let the vector bundle, which solves the Hermitian-Yang-Mills equations, be the tangent bundle. In this case, deformations of the vector bundle correspond to the complex structure moduli of our Calabi-Yau. And we can compute the metric on the complex structure moduli space. This is the Waller-Petersen metric. And using the Waller-Petersen metric, we can compute the normalized Kala couplings without reference to the Ricci flat metric. This shortcut to elide knowing the Ricci flat metric in order to normalize these Kala couplings only works in the so-called standard embedding. The constructions of standard model-like theories by the Penn groups in the early 2000s, these are non-standard embedding constructions. In fact, most of the string standard models that exist today are non-standard embeddings. I'll make some comments about how to calculate things there at the very end, but we're working in the standard embedding. So in other words, we're requiring the chi equals plus or minus 6 in order to get a standard model-like theory for the string compactification. So to normalize the Kala couplings, we construct an orthonormal basis with respect to the Waller-Petersen metric, and we can do this in multiple ways. One way is one which invokes the Kodaira-Spencer map, which takes the deformations on the base space to some cohomology, and we can use a harmonic projection in order to implement this idea. And using this Waller-Petersen metric, we can calculate the normalization that we need for our fields. So in the standard embedding, the normalization is given to us by this Waller-Petersen metric. We essentially pick an arbitrary basis, apply Gram-Schmidt, and we take the previous expression, the unnormalized expression, and we normalize with respect to the numbers we obtain in this diagonalization. In cases where there are not a large number of moduli, we can also compute the Waller-Petersen metric from direct computation of period integrals. And Morrison explained how to do this, and Candelas, Delosa, Green, and Parks use this idea as well to compute the Waller-Petersen metric using these period intervals. So there are different ways of computing this Bala-Petersen metric from which you can get this normalization. So for the Dwork quintic, the period integral is something you can do for any value of the complex structure modulus, and the Kodaira-Spencer map is implemented for particular values of this complex structure modulus, and we see the two results agree. So a particular point in the moduli space of the quintic is the Gepner model, and in this particular case, we're able to, Distler and Green computed the Icala couplings as powers of some ratio of gamma functions. And the comparison that we make with these Icala couplings using the Bala-Petersen method obtained from the Kodaira-Spencer map essentially lies right on top of the expected numbers that we predict. So these numerical methods, in this case, agree. In the case of the quintic, we can also compute the same couplings using the machine-learned Ricci-flat metric. We essentially implement a loss function that ensures harmonicity. And we find that the Bala-Petersen method that we use with these harmonic forms agrees to several decimal places to the exact answers we get for the period intervals. So this is a corroboration that the Ricci-flat metric is giving us the expected answer in the cases where you can compute these things many different ways. If we take the mirror of two cubics in P5, their intersection, we find the manifold has H21 equals 1, and we can compute the Bala-Petersen metric of the normalized Icala coupling in this theory using period intervals and the Bala-Petersen method, and we find the Kodaira-Spencer map agrees with the period intervals. This is sort of a cross-section of the previous plot, and we see the points lie on top of each other, even very close to the singular point at psi equals 1. So in this case, we compute these things in many, many different ways, and this is the comparison of the previous calculations along with the choice of harmonic representative using the Ricci-flat metric. And again, all these different methods of calculating, they all agree. We can use this then to compute the Icala couplings, and the Icala couplings, they're the different methods of calculating these, they give us roughly the same answer, even close to the singular points. Okay, so we'll move on to Tian-Yau quotient, which is used for phenomenology. This is the explicit realization of the Z3 quotient, and we get this manifold with order character -6. And Kilara and Mahapatra studied this string construction back in the day. So along one direction of the moduli space, by the Kodaira-Spencer method, we're able to compute the Bala-Petersen metric. And we can compute the Icala couplings, the unnormalized Icala couplings, and normalize these. And this is what we did. We had the expected unnormalized results, which we normalized. And we find that the normalization shifts the value of the Icala couplings. So this is the amount of this shift, the Tian-Yau quotient. So here we consider ratios of Icala couplings as a function of this complex structure modulus epsilon, and we find that these Icala couplings change depending upon where you are in moduli space. One thing which is of particular note is that small excursions, the previous one was ratios Icala couplings, these are direct values Icala couplings. The important point to note in this plot is that with small excursions from symmetric points in moduli space, we're able to obtain hierarchies in the Icala couplings. So the Icala couplings here, these differ by several orders of magnitude. So these hierarchies in Icala couplings will lead to mass hierarchies in the action in 4 dimensions. So the fact that there's a light generation, a medium generation, and heavy generation in the scalar model may not be an unnatural feature of string compactification. This might be a natural result in moving away from symmetric points, we obtain these hierarchies of masses. So this is very encouraging for the program of stellar model building from string theory. We can also see what happens to these couplings near singular points. In the moduli space, you find that sometimes all these couplings vanish when they're normalized. at the singular points, for example, at -1. So let me summarize and discuss prospects and tell you about how to reproduce some of our results. So we've produced Ricci flat Calabi-Yau metrics on K3 in various threefolds. We've computed Yukawa couplings, both unnormalized and normalized. The methodology we produced works for any SISI on any value of H21. The standard embedding can compute these couplings in various ways, and we get essentially the same answers in all of these approaches. So we'd like to track what happens to the change of complex structure moduli to better understand the origin of hierarchies. We'd like to compute these Yukawa couplings for toric Calabi-Yaus in addition to continuous section Calabi-Yaus we've looked at. We'd like to move on to non-standard embeddings, work by the Oxford group, Andre Constantine, Andre Lucas, and their students have already studied this in certain cases. They also see that the generation of hierarchies in the non-standard embeddings. So again, this may be a general lesson for string phenomenology that these mass hierarchies are maybe not so difficult to realize. We'd like to eventually move on to test the phenomenological virtues of the approximately million string standard models that are proposed and see whether any of them reproduce the masses that we see in nature. And hopefully this will lead us to some first principles calculation of electron mass and string compactification. So let me discuss how we can do better and how this relates to point selection. So to do this, let me mention an old paradox called Bertrand's paradox. Bertrand's paradox asks for the right way or the best way to pick a random chord on a circle. So one way to do this is to just pick 2 points on the circumference and draw a chord between them. Another way to do this is to pick a random radius and then choose a random point on that random radius and draw the perpendicular to that point you've selected. A third way of doing this is to pick the random point in a disk and have that random point be the midpoint of a chord. All of these methods are random in that they exemplify a principle of indifference that Bertrand proposed. So the distributions of chords chosen using each of these methods is completely different, of course. So you see that the distributions just visually look different in the 3 cases. So the question Bertrand proposed to answer was, what is the probability the random chord is longer than the length of the side of an equilateral triangle, which is described inside the circle? And these 3 different ways of choosing give you different answers. So you can convince yourself the probabilities are 1/3, 1/2, and 1/4 in each of these 3 ways of choosing chords that I mentioned. So Jaynes proposed a solution to which is the best way to choose these random chords. And Jaynes observed in the statement of the problem, we don't specify the size or position of the circle. And as a Bayesian, he argues the distribution should be scale and translational invariant. And of the 3 methodologies I proposed, only the middle one, random radius, random point, draw the perpendicular, satisfies this these invariances. So you can see, for example, obviously the third one, if you move that circle around, you get a totally different distribution. The comparison to make is by choosing 2 random points on the circumference, the first method I proposed. This is like the fiber bundle Hopf map that's used to choose points by a la Schiffman-Zelvich. It's the analog of taking points in the ambient space and drawing a line that we're looking at. So if you compare a different way of choosing points, which we can do for T2, where we know what the right answer is, we know that we can map T2 in various forms to a fundamental domain. We can choose points randomly in that fundamental domain on the complex plane. If we choose the points using the flat metric, in other words, we get a different distribution of points than if we choose using the Schiffman-Zelvich approach. And these are the 2 distributions you have for the point selection. If you use points selected in these 2 different ways for training to get the flat metric, you find that the second way of choosing points with respect to the flat metric to begin with is 2 orders of magnitude better in approaching the flat metric after a similar number of epochs. So if we can improve the Fubini-Study point selection even slightly, this may give us a large improvement in how well we get to a flat metric. And we're thinking about ideas for better methods of point selection in order to do this job. So that's one way of maybe improving a lot of these results. With a better point selection, we can get flatter and flatter metrics, and therefore we can apply these flatter and flatter metrics more efficiently to the various problems we're considering. Okay, so earlier this week, we released our code base. We call it CIMIC, Calabi-Yau Metrics, Ecologies, and Curvature. The name is Mirror Symmetric. That's the GitHub site for our code, and you're very much invited to play with the code and see how we do many of the calculations that I mentioned in this plot, and of course in this talk. And of course, if you find bugs, please let us know so we can improve this. So with that, I'll thank you, and I'll ask if there are any further questions.